All right, well, welcome everyone. This is Introduction to PASCO Capstone, and over the next 60 minutes, I plan to show you some of the fundamental capabilities of Capstone for connecting PASCO sensors, collecting data from them, visualizing that data in a variety of displays, and doing analysis on that data, and we're delighted you're joining us today. So to do that, I have three activities planned. I'll demonstrate a quick activity on mass on the spring. We'll look at the position of that mass over time, and in doing so, learn about how we can connect sensors, collect data from them, and visualize that data, particularly in a graph display. Next up, we have planned to do impulse momentum. This will be the main activity we're doing today. And in impulse momentum, we'll take a deeper look at how we can control what measurements are being made and how they are being made to make sure we capture the data of interest. And we'll also do a much deeper dive into analysis, particularly the ability to do analysis in the graph display. Finally, the last activity is a quick one where we'll learn a new technique for gathering data called manual sampling, and we'll be able to associate user-entered data that we type from the real world with measurements made from a pressure sensor as we investigate the relationship between gas pressure and volume. And we'll also look at how we can transform those measurements to do analysis inside Capstone. Throughout, Alec will be answering the questions that are coming in the Q&A. We will pause with interludes to highlight some of those questions that may be of interest to everyone and in the recording. And then we'll discuss some interludes, saving files, how do we share data from Capstone, what sensors can be used with Capstone, and I'll point you to some experiment resources where you can see hundreds of experiments that are ready for your students to use with Capstone. So a quick introduction to the software itself. PASCO Capstone is our advanced data collection, display, and analysis software for all PASCO sensors. Although it is used across the sciences, it is particularly tailored to the interests of upper-level secondary and college university courses. And it has many capabilities which are kind of tailored towards physics and engineering. So although it's used across the subject areas, it is particularly useful to physics and engineering classes at the upper high school and above levels. It takes advantage of the fact that we're on a computer, so it's available for Windows and Mac OS. It does take advantage of large screens, mouse capabilities. We have other general data collection software, particularly SparkView, that is functional across all of the platforms used in education today, from phones to tablets to Chromebooks. But Capstone is specifically designed for Windows and Mac computers. It's available as a free trial, so for the 30% of you joining us today who haven't had experience with Capstone, if you don't have Capstone, we invite you to go to our website and get the free 30-day trial. It's fully featured. It just times out after 30 days. There are options to purchase Capstone. The current options are a site license, which is a one-time purchase that entitles you to use Capstone in all the computers managed by a K-12 school or by a university or college department. It's a one-time purchase, so those of you who are at schools that purchased when Capstone came out in 2012 are still getting free updates of Capstone now that we're on version 2.9. The other option is a fairly new one, and this is a personal license. Personal licenses are roughly a US dollar in your local currency if you're not in the US, and it's good for 1 year. It does not auto-renew, but you can, of course, purchase it again at the end of that year if you'd like to use it for another year. And it's available globally through the Microsoft Store for Windows or through the App Store for Mac OS. And you can get more information about Capstone, including a link to that trial, at pasco.com/capstone. All right, so let's dive into the first activity here. Let me show you what I have set up, and that is simply a couple of masses totaling 200 grams on a vertical spring, and I can set those in motion. And the question I'd like to answer using Capstone and a sensor is, how can we quickly collect and visualize sensor data to show us the position of those masses over time? So to do that, we're going to be using a wireless motion sensor, one of our sensors in the wireless line. And the wireless motion sensor works a lot like a bat or a dolphin's echolocation. It sends out chirps of sound from this transducer. They happen to be ultrasonic, but they go off and then it listens for the reflection of those sounds, echolocation. And from the speed of sound and that round trip time, it can determine the position of objects in front of it. And it can also drive the velocity and acceleration. So how do we use this with Capstone? Well, let's jump into Capstone. I'm going to launch Capstone. And let's take a look at how we can quickly connect this sensor to visualize the measurements coming from it. So when we launch Capstone, it presents us some tiles. These are some quick start options for popular ways to use Capstone. I immediately see this top tile called Sensor Data, and if I hover my cursor over it, you'll see that it tells me in a tooltip, this allows me to connect my sensor and record data in a graph. That sounds perfect for what I'd like to do here, so I'm simply going to click on the Sensor Data tile. And Capstone is going to do a couple things. It's going to give me a big graph in the background there. And importantly, it's going to open up what we call the hardware setup panel, which is a prompt for me to connect my wireless motion sensor. So let's figure out how to do that. The wireless motion sensor, like all our wireless sensors, has a built-in battery. So I'm going to turn the power on to that sensor by pressing the power button. After I do that, I can see on the sensor that there is a Bluetooth light, and it's currently blinking red, indicating that this sensor is available to be connected to Capstone. Now, to better simulate what happens in your classroom, I'm going to turn on another motion sensor that I have on the table next to me. And we can see that all the available PASCO wireless sensors show up in the hardware setup panel under a title called Available Wireless Devices. So just as in your classroom, I need to figure out, well, which of these sensors do I want to connect to, which would be appropriate for me. So what we can do is look at the sensor itself. And on the sensor case, there is a 6-digit ID. And that 6-digit ID is going to correspond, hopefully, to one of the sensors that you see here. In my case, it's that 003-183. So all I need to do is click on that in the available wireless devices list. And when I do so, Capstone is going to make a wireless BLE, Bluetooth Low Energy connection to that sensor. And on the sensor itself, I can determine that I've connected to Capstone because the Bluetooth light is now blinking green, and this sensor is no longer available to anyone else in my lab to use it. And we can also see in Capstone's hardware setup panel that it has moved to the top of this list here. It is now a connected device in this list. So now that I've connected my wireless motion sensor, I'm going to place it under the mass here and make sure I line it up fairly well with the transducer facing up toward the bottom of that lower mass. All right, so I'm going to close the hardware setup panel simply by tapping on the button here. And the important thing that's happened in the background is Capstone has taken that graph, realized we've connected a motion sensor, and it selected the primary measurement from that motion sensor and placed it automatically on the y-axis. So that's position coming from the motion sensor, and it has defaulted to position on the y-axis of this graph and to time on the x-axis. We're going to see shortly we can change those, but that's exactly what I'm looking for if I'm interested in the position of these masses over time. So before we actually begin collecting data, let me give you a quick tour. This main white space where we are going to collect data and visualize it and do analysis is called the workbook space. And to the sides of the workbook, we have what we call palettes. To the left is the tools palette, and we saw that this includes the hardware setup panel. It also includes a data summary panel we'll look at. Below the workbook is the controls palette, and the controls palette is where we can choose to record and stop recording data and choose the setup of our sensors for data collection. And finally, although it's hidden now on the right, I'm going to open it up, and we have a displays palette that will let us later in today's webinar take control over which displays we're using to visualize our data. But let me now set these masses in motion above the motion sensor, and I just need to start collecting data now from the sensor. And to do that, I'm going to go down to the controls palette where I can see a big red record button. So I'll press record. And we can see immediately that when I press record, we start getting position versus time data plotted here in the graph. Each of those dots is a position measurement, and you can see that by default they are connected by straight lines, so we can follow it a little better. You may also notice that when we reach the right end of the graph, it automatically scaled. Capstone's graph default behavior is to always show us all the data that's being recorded. I think that's plenty of data, so I'm going to return to the controls palette and press this red stop button. Now, all of the data we collected between pressing record at experiment time 0 and pressing stop at experiment time 25.9 seconds comprises what Capstone calls a run of data. And Capstone names the runs run number 1, run number 2, etc. And we can see that from the graph legend up here, we have a run number 1, and Capstone has given it a default color and unique symbol, so we can distinguish it if we collect future runs. All right, so we saw that Capstone automatically scaled the graph for us in time, but we may want to improve our view of this data. It's not doing particularly well on the vertical y-axis here in terms of taking advantage of all our screen real estate. So let's figure out how we can change the view of data in the graph. One thing we can do is just take our cursor in the form of a hand here, and just like you can with a physical piece of graph paper on the tabletop, you can just translate it around by clicking and dragging left, right, up and down, and this allows us to move this graph around to change what's in the middle of our view. More interestingly, and something you can't do with traditional graph paper, is you can put your cursor over the numbers on the y-axis or the x-axis, and you'll get a two-headed arrow, and this allows you to click and drag and essentially stretch this out as if the graph paper is made of rubber. You can expand it, you can compress it each time going toward the origin, and that same technique works for the y-axis or the x-axis. So through a combination of panning in the middle And stretching on the axes, you can change your view of the data to look at whatever portion of it you'd like. Now, if you happen to be on a laptop with a scrolling trackpad, or you're using a desktop computer like I am that has a scroll wheel on the mouse, you can take advantage of that scroll capability. I use this a lot. In the middle of the graph, you can simply hover your cursor over a data point, and you can scroll in or out directly toward that data point. And a similar technique of scrolling works on the axes. If I hover over a particular data point on the, or rather a value on the axis, the y-axis, I can scroll in or out, and you can see it scrolls only that dimension, only that axis. So this is a great way to change your view of the data. All right, so we can pan, we can scale, but oftentimes our goal is simply to have the data fill the graph screen. So for that, we're going to go to the graph toolbar, and we're going to introduce you to one of the many tools we'll look at in the graph toolbar today. Now, you may or may not see a graph toolbar. It depends on whether your cursor is away from the graph or over the graph. It appears and disappears, just to avoid clutter. But since we're going to focus on the graph toolbar today, I'm going to pin it with this orange pin to make sure it's always visible so we can look at it and always have it there. And I'm going to introduce you to the leftmost, probably the most used button. And I can hover my cursor over this button, and we see that it says what this button will do. It will scale axes to show all data. Now, it's important to note this button actually has two parts. There's the icon on the left, and there's a black drop-down arrow on the right. So if I want to enact this scale to fit action, I'm going to press the left part, and we can see that it automatically moves the data and scales these axes so that the data fills the screen. Now, many of the buttons in the toolbar have two parts, including scale to fit. If I click on the drop-down part, you're going to see options for the button's capabilities. In this case, there's only one option, and that is to auto-scale from 0, that is from the origin. So if I turn that on, from now on with that feature on, when I press the left part to enact scale to fit, it's going to include the origin. Now, if I don't want that, I can simply return to the drop-down, which lists the options, turn that off, and from now on, the left part, the actual scale to fit button, is going to scale just to fill the screen with data without regard to the location of the origin. Well, let's look at another button in the graph toolbar that has two parts, and this is the statistics button. It looks like a red Greek letter sigma, and it again has two parts. The left part, if I press on it, is simply going to turn on statistics. In this case, it defaults to showing me the mean value of all the data points throughout run number 1, and it shows this to me visually, indicating where along the y-axis that value of 0.23 meters lies. The right portion, the drop-down of this button, allows me to choose which statistics I'm looking at. So I might choose to turn on minimum, maximum, mean, standard deviation, and all 4 of those statistics are now displayed visually on the graph. And again, I can use the left part, the statistics button itself, to toggle on or off the visibility of those selected statistics. So that's how the two-part button works in Capstone's graph toolbar. All right, I'd like to record another run of data to see how the graph and Capstone behave when we collect multiple runs. I'd like to change something about this, so I'm going to remove one of the 100-gram masses, so I'm left with just 100 grams on the same spring. And I'm going to set that in motion. It may be a little off screen, but you can see it bobbing in there on screen occasionally. And to record a second run of data, I simply go down to the controls palette once more, press the record button, and I can see in the graph I'm now collecting what's called run number 2 here in the legend. I'll let that go for a few seconds. And as I do, you may have immediately noticed what happened to run number 1. We'll talk about that in a second. I think I have plenty of data, so I'll press stop to end the recording of data for run number 2. And now I need to tell you where data actually lives in Capstone. It doesn't live in the displays, they're just a way to see it, but all the data in Capstone lives in the Tools palette Data Summary panel. So if I want to know what happened to run number 1, was it deleted, does it still exist in this file, I'm going to go open the data summary, and I can see from the wireless motion sensor that it has actually given us readings of position, velocity, and acceleration. That's what's been recorded. And indeed, I have run number 1 and 2 for all those measurements. So run number 1 still exists in this file. It's simply not being shown in the graph currently. Well, the data summary is great for figuring out what data you have. It's also great for giving names to that data that's more descriptive. So I'm going to double click on run number 1 here. I'm going to keep run number 1 just to keep things in order, and I'm going to actually change the name so it describes what was happening here. I'll put -200 grams, and I'll hit enter. I'll do the same and double click on run number 2, and let me remind myself by changing the run name that this was 100 grams. Now, when I hit enter here, I want you to look over to the right. I'll hit enter and notice that the run was renamed throughout the file. So kind of proof that the data is living here in the data summary. That name change of the run is going to propagate throughout the file wherever this run appears. All right, so let's collapse the data summary and return to this question of why did the graph only show one run at a time? Well, that's the graph's default behavior to keep things clean, but we can choose which run is being displayed in the graph and actually change that behavior using another two-part button. This is the data summary button. It looks like a rainbow triangle. I'm going to start with the drop-down portion. And if I click on the drop-down, you'll see a list of all the runs that could be displayed on these axes of position versus time. Currently, I'm showing the most recent run, run number 2, but if I click on run number 1, the graph switches to show that. You'll notice it turns off run number 2, and that is the purpose of the data summary button itself. With the data summary button up, it only shows one run at a time, but if I click and depress the left portion of the data summary button, with that on, I can now return to the dropdown and choose to show multiple runs at the same time. And for convenience, there's also a select all option there. But it's helpful to know the different behaviors of the two parts of this button. So now that we're looking at both run number 1 and run number 2 at the same time, you might begin to notice some differences. Of course, they had a different equilibrium point when I went from 200 grams down here to 100 grams up here. You may also notice something more subtle, that it looks like the period or the frequency has changed. If I want to explore that a little more, I might use different approaches to figuring out what the period or frequency is. I'm going to jump to the perhaps most advanced one and say, gee, it would kind of be nice to fit a curve to these and see if we could determine what the parameters of that data is from a curve fit. So for that, I'm going to introduce you to another graph toolbar button. And this button is interesting because it is called the curve fit button, but the left part of the button is already on. Why don't I see any curve fits? Well, it's because the curve fit has not been selected yet from the right drop-down portion. So I'll click the drop-down right portion of the curve fit button, and you'll see over a dozen different fits we can choose from, including essentially an infinite number. We can define our own. In this case, I'd like to try a damped sine fit. So I'll turn that on, and you can see in the background that it has done its best and done pretty good job of fitting a damped sine fit to run number 2. And this is essentially the product of an exponential decay and a sine fit. And this label shows me the parameters of that fit. Now, it would be reasonable to ask, well, why did it only analyze run number 1? Well, we only have one graph toolbar, and we have to figure out what run, if we have multiple runs, does this graph toolbar apply to. It turns out that it applies to, by default, the most recent, and we know that by looking at the legend here. So if we look at the legend, you'll notice both runs listed, and only one of them, the most recent run, number 2, is active, as we call it, and that's indicated by a shaded background behind the symbol for this run. So the most recent run is active by default, and that's why the damped sine fit applied to run number 2 only. If I want to make a different run active, I'll go to its symbol in the legend, or alternatively, I can click on a data point of that run itself in the graph. It becomes the active run. So now with run number 1 active, I could return to the dropdown for the fit, and choose the same damped sine fit, and we can see it making a different fit, but successful fit to that one. So now we could pursue what's the difference in frequencies, for example, to explore these different these changes in period or frequency when we change the mass. All right, so that's kind of an introduction to how we connect a sensor, how we visualize the data from it, do some analysis, and most importantly, how we control what's being shown in the most used display for most experiments, the graph display. Now, I want to show you one other thing. You may recall that the data summary showed us that we had both position, velocity, and acceleration. By the way, you may ask, can you make more than one run active at a time? It turns out you can by shift clicking or by clicking on the header here. So if I wanted to hide all my fits, I could make sure all the runs are active, and I could come back here and toggle these curve fits on and off with the left part of that curve fit button. What I'd like to do now is explore some of the other measurements that were made. Instead of position on the y-axis, which looks right now it's just a label, but that label is indeed a button. So I could click on the y-axis label of position, and I'll get a drop-down menu that allows me to switch it to something else like velocity. So here are the velocities for run number 1 and 2 as recorded by the motion sensor. Now, graphs in Capstone default to time on the x-axis, but you can change that as well. This is once again a button, so I could go under time, and I could even choose a measurement from a sensor. So for example, position, and now we can see I can get something like a phase plot of both of these runs with 200 gram mass in green and 200 gram mass in blue and 100 grams of mass in green. So we can see that we can manipulate how we're viewing the data in this very versatile graph display and do some quite sophisticated analysis with it. So I've saved my favorite Capstone feature for the end of this activity, and that is the following. Capstone has unlimited undos. So if I didn't like the last thing I did, I could come up to the Edit menu and choose Undo Plot Area Pan, or I could choose this blue backwards arrow to undo that. Or since I undo so many things, I'm going to remember this keyboard shortcut, Control-Z on Windows, Command-Z on Mac, and I can step back and undo an unlimited number of steps. So I'm going to press Control-Z, Z. You know what? I'm just going to hold Control-Z, and we're going to see Capstone go all the way back to the beginning. And if I look at that Edit menu, I can redo with Control-Y on Windows or Command-Shift-Z on Mac. So I'll press Control-Y, and it's going to step through everything that was done in this file, including the data collection, analysis, changing of the displays. So although Capstone's designed to make it easy for you and students to explore the world around us, I'm hoping you realize that this undo capability will hopefully allow you to experiment with the features of Capstone and not be trepidatious about trying what that button does, knowing that you can always undo it. All right, so that's an introduction to Capstone and probably the features you are going to use most in Capstone. I'm going to return to my slides for a moment and talk about one of three ways we're going to look at today for saving and sharing your data in Capstone. The first is the most fundamental, and that is simply saving the PASCO Capstone file. It's going to have the extension .cap, and this is going to preserve everything about the file. So returning to Capstone, I can save this file by going to the File menu, choosing Save Experiment. I'm going to save it with a name like Mass on Spring. And you'll notice this is going to be a .cap Capstone file. I'll save it to my desktop. And now I could close Capstone. I could send this file to Alec, even if he's on a Mac and I'm on Windows. And as long as someone, the recipient, or you have Capstone on a computer, you could always open up Capstone, as I'll do now. Go to the File menu, choose Open Experiment, and I'll direct it to that Mass on a Spring file. Open that up, and you'll see that all the displays, all the analysis I would have had are still in this file. So saving a file as a .cap Capstone file is the most complete way to preserve everything about it. I could now continue my analysis, share it with someone else. I could even reconnect a sensor and collect more data into this file by saving it as a Capstone file. All right, Alec, any questions we should bring to the attention of everyone?
No questions so far, but if you do have any questions, feel free to put them into the chat.
Great. Thank you, Alec. All right, so I used a wireless motion sensor for this. We have dozens of different sensors for measuring things from position to voltage, current, forces, things like that. But over the years, we have had many different lines of sensors. We have the wireless white sensor, like the one I'm using here on screen, but we also support in Capstone all the previous generations, including the Passport line of sensors that came out in the early 2000s. You can probably tell from their translucent blue cases generally. And Capstone supports also our Science Workshop sensors, which came out, it's funny to say, in the last millennium. So these are probably older than your average student from the late 1990s. We continue to produce some of them, but the bottom line here is that Capstone supports all these lines of sensors that you may have in your lab. All right. So the important thing to know is that the wireless sensors can be connected via Bluetooth Low Energy, as I did in Capstone a moment ago. They can also often be connected via USB directly, but for these other lines of sensors, Passport and Science Workshop, you will need to have an intermediary we call an interface that allows you to plug the sensor into the interface and connect the interface to the computer with Capstone on it. These range from the simple AirLink with just one channel to the most powerful 850 universal interface with multiple ports, supporting both Passport and Science Workshop. All right, you can learn more about the sensors at pasco.com/sensors. I see a question from Andrew. We are indeed going to cover how to get images out of Capstone as the third iteration of how to share data from Capstone, so thank you for that. All right, so let us jump to the second activity. I'm going to rearrange things here. Alec, anything we can address as a group as I change the physical setup here?
Yes, I just answered a question from David about selecting part of your data set to fit a curve to. That's through the Data Select button.
Yep, that is a great question. We are actually going to cover that in this next activity. So thank you for that preview. All right, so on the live video feed here, by the way, you can change the relative size of the video and screen sharing if you're here with us live. I have a smart cart. The smart cart is essentially a suite of sensors on a low friction cart, built into the low friction cart. We're going to use a few of the measurements, the many measurements available here, but I've placed this cart on a horizontal track and I've attached to its force sensor a hard spring, as you can see both in the live video and in the photo on the slide. So in this round of investigation, I'd like to try to answer these questions. How can we control the sampling options to ensure that we're capturing the data we want? To investigate, in this case, the relationship between impulse and momentum. And how can we analyze that data in depth to derive that relationship, hopefully? So what we're going to do now is jump back into Capstone and try to answer those questions. So I have the previous file open. If I want to start a new file, I could either close Capstone, relaunch it, or simply go to the File menu and choose New Experiment. Capstone likes to have just one file open at a time, so the previous one goes away. It'll prompt you to save it if it wasn't saved already. And I begin a new Capstone file. We could indeed begin once again with the sensor data approach from the startup options, but this time around I want to take more control of how we set things up, just so you know that we have that control in Capstone. So instead of using one of these startup buttons, I'm going to go directly to the hardware setup panel. I'll open that up and we connect the smart cart just like we do any other wireless sensor. It's not white, but our blue and red smart carts are wireless sensors. So I'm going to turn the power on to the wireless smart cart, at which point you can see it shows up in the list of available wireless devices in Capstone's hardware setup panel. So this is indeed my smart cart by the ID, so I'll click on it to connect. We're going to see in a moment the smart cart offers many different measurements, only some of which we're interested in this case. But once this cart is connected, we'll see that it is actually indeed a suite of sensors built into the cart. It includes a position sensor, which is the rotation of the wheels measured by an optical encoder. There's a force sensor, a 3-axis acceleration sensor, a gyro sensor. And although we can collect data from all these sensors, it's going to turn out that for this activity, I only want measurements from a couple of these sensors. Now, if I hadn't used this before, how would I know which measurements are available from which sensors? Well, I can go to the data summary. And even though I haven't collected data yet, we can see that each of these sensors built into the smart cart is listed, and the measurements provided from that sensor are listed below as well. In this activity, I'm interested in velocity and force, so I don't really need to use the acceleration sensor and the gyro sensor. If I know I'm not going to use them, I'm going to return to hardware setup, and I'm going to switch them off, so these sensors will not be reporting data. If I don't switch them off, all sensors data will be recorded into Capstone. In this case, I want to preserve the bandwidth here for the measurements I do care about, so I'm turning off acceleration and gyro. All right, so I'm done with hardware setup. I'll collapse that, and let's return to our workbook space, where this time I'd like to take control over what displays we're using to visualize the data. And for that, we'll start with the displays palette to the right of the workbook space. If I hover over a display, you'll see the tooltip tells me there are two ways to add this display to my workbook. One is to drag it to the page, and the other is to double click it. I'm going to begin with that double clicking, so I'll double click on graph. And by default, the graph I chose by double clicking fills the screen. Now Capstone doesn't know which of the many measurements to show on this graph, so instead of showing a measurement, it just shows me the button telling me to select a measurement for each of the axes. If I start with the y-axis measurement and say choose force, you'll see that the x-axis defaults to time. We know we can change that if we wanted to, but in this case I would like to begin by exploring these force measurements to see if we're properly set up to record the type of data I think we'll need in order to investigate the relationship between impulse and momentum when the cart does the following. It undergoes a brief collision with some object like the wall. So I have the force sensor measurement graphed here. I'm simply going to take the defaults and say, can I just use the data as it comes? To do that, I'm going to press record, and I will push the cart into the wall there and let it bounce off with this hard spring that I have connected to its force sensor. So I'll press record, push the cart, press stop. I'm going to scale to fit, and I'll ask those of you who are live with us to critique this. Is this data, this force versus time data, representative of the forces that this cart experienced during that brief moment of collision? If not, what would you change? How do you criticize this data? So let's be critical consumers of our data here. This is simply the default settings from this cart. force sensor measurement. And we're going to learn in a moment that if we want to change something, we probably can. So let me know in the chat if you have any thoughts on what could be improved. Andrew says, without friction, then yes. Okay. All right, Shihan and Michael, I think, have similar ideas here. Yeah, I'm going to zoom in here using that scroll technique on the x-axis. And what I'd like to note is that I think the collision happened in this time span. The force is close to 0, and then it goes negative. But notice I have only one force measurement that occurred, what I think is during the collision. I would really love to know what was happening in between these data points. So I'm going to do what many of you are suggesting in chat, and that is I'm going to try to record more data every second, which we call the sample rate. So thank you to all of you who had suggested that, Diego as well. Yeah, David, it's interesting. This is just one force measurement. It happens to be there. But we're going to see in a moment we have very good control over that. So whenever I'm dubious about is that enough data, I often go in and collect another run. Now, any more subtle critiques of this data? If so, let me know in the chat. One critique that sometimes comes through is, why is this force negative? Well, it's negative because the force sensor on the smart cart has a convention that's shared by all the measurements from this. And that convention is shown on the cart label itself with a XYZ axes. And although it might be tough for you to see, I can see that the x-axis positive direction is toward the right, as you currently see. On newer smart carts, we've also labeled that plus X with this large arrow, but in either case, you can look at the 3 dimensions here. And this is how the cart reports positive and negative in all 3 dimensions for things like acceleration. So the positive X direction is this. That means the force that the cart experienced is negative. Now, I could change that, but I don't want to have to change it for all the measurements. So we're going to go with that because it's going to be shared, that convention will be shared by all the cart's measurements. Let's see. Yeah, Marie mentioned that. So there is one more subtle thing. This cart is actually pretty good on this. But if I zoom in, you may notice that the forces measured by the cart before the collision and after the collision are not quite 0. They're just a little bit above 0. That may or may not have a significant effect on our analysis. But I'd like to define the cart's current measurement of force as 0 when it's not undergoing a collision. And to do that, we're going to go down to the controls palette. So we're going to do 2 things in the controls palette. One is change the sample rate of these measurements, how frequently they're recorded. And the other thing is we're going to 0 the force sensor with no force applied to the sensor. So you'll notice the smart cart position sensor is currently visible here. I could come in and choose a common rate, but I want to adjust each of these rates separately. This is one of those experiments where it's nice to have control separately over the different measurement sample rates. So I'll select smart cart force sensor. I see that its default sample rate is 20 Hertz. That's 20 recordings every second. I'm going to bump that up, and I can use the up and down arrows to change that. And from prior experience, I know that if I increase it fairly significantly from 20 Hertz to 500 Hertz, I'd expect many more data points during that short time span. That's about 1/10 of a second here. All right. Now, while I have smart cart force sensor selected, next to the sample rate selector, you'll notice a 0 sensor now button. So I'm going to make sure there's no force applied to the cart spring right now. I'll press 0 sensor now. It's now going to define that in this experiment to be 0 newtons. All right. Now, it turns out I also want to change the position sensor's sample rate. This is giving us data that we'll look at later for position, velocity, acceleration. So I'm going to select it, and I know from experience that if I just bump this up a little bit to 50 Hertz, that's plenty because I'm primarily interested in what's the velocity of the cart coming into the collision and exiting the collision. We'll see some detail about during the collision, but what I really want is before and after. All right, I've defined the sample rates as I think I want them. I'm going to delete this run that I was just using as a trial, and I can do that very quickly in the controls palette as well using this delete last run button. So I've gotten rid of that run. I could, of course, undo that if I hit it by accident. But now with these new sample rates, I am ready to collect another run of data. So I'll return to the controls palette, press record, push the cart into the wall, press stop. And now let me use the scroll technique on the x-axis to really zoom into that section during the collision. And now we can see we have 20 or so data points during that collision. And I think that's probably a much better representation of the forces the cart was experiencing during that collision, which is what I'm really interested in this investigation of impulse and momentum. All right. And I can also see that the force appears to be much closer to 0 before and after the collision, where afterwards that spring was vibrating a little bit, and thus the oscillations there. All right, so we're going to do some analysis on this force data, but first I want to see a little bit more about the position sensor readings. And for that, I'd like to take a look at the velocity of this cart before and after the same collision. Well, I know that velocity data was recorded. I can confirm that in the data summary. I just need to have a way to visualize it. I'm going to show you some ways we could do it, and then I'm going to end with what I think is the most appropriate way. We're going to return to the displays palette first, because if I want another graph, I would intuitively come over to the graph and I could double click another graph. And by default, it's going to put this graph to the right of the current one and shrink the other one so they're not overlapping. And I could choose velocity for the second graph, but there are some downsides to this. This would work, but notice that these graphs are unrelated to each other. We have different X and Y axes. I'd really like those X axes to be shared so that I can scroll through the data in time from both measurements. So let me undo that, Control Z, Control Z, Control Z. And the other option for adding displays is to click and drag. So if I click and drag, you'll notice I get these blue boxes, and these blue boxes tell me what would happen, where this new graph would be added if I release. So let me release it before the existing graph and make this velocity time. And I can see this looks better, but still, even though I have time axes, they're not aligned because these are two separate graph axes, rather two separate graph displays. So I'm going to undo that again. And I'm going to show you what I actually like to do. Whenever I want to make sure things are nicely synced and I want to show multiple measurements, I come up here to the graph toolbar and I see there are a couple of options. I can add a second y-axis, or what I'm going to do in this case is add a second plot area. I'm going to do this and then we'll explain what plot area is. So I'll add a new plot area to the graph display. I still have only one graph display from the perspective of capstone displays, but it is now divided into two parts, an upper plot area and a lower plot area. The upper plot area is force. I can assign velocity to the lower plot area. And now what's really nice is notice they have a shared X or time axis. So I could quickly scroll in and take a look at that collision, and these two data sets are visualized in sync in time. So I really like this ability to have a new plot area when I'm looking at two different measurements that have different units, like force in newtons and velocity in meters per second. All right, so one final thing, we're going to analyze the change in motion from the velocity data, and we're going to analyze the force applied, the impulse from the force curve. But I'd like to swap these two plot areas so that velocity is at the top, force is at the bottom. I could simply switch each of these, but it's a little quicker. I can't really pull them because that is moving the graph itself. But if I come up here to the graph toolbar, there's a button that allows me to go into rearrangement mode. If I click on that, I can now grab one of the plot areas, drag it below the other or above the other. And when I release it, they swap, and I can turn off rearrange mode now to have them in the order I prefer. All right, so let's begin with asking the question, how did the velocity of this cart change from before the collision to after the collision? And we could read the values off of the graph axes, of course, but as you can probably guess, there's a tool that would let us do this a little more precisely. And that tool is called the coordinates tool. It has a little crosshair in the toolbar. I'm going to turn on the coordinates tool and choose add a coordinates delta tool. And I see that it is applied to this plot area as I wished. Now, let me show you that sometimes that won't happen because we have two legends, two plot areas, but we still have only one graph toolbar. So we have to recognize that not only do we have the notion of an active measurement or an active run, we could have both these active, but we have the idea of an active plot area. And the active plot area is the one shown with a cyan border around it. We can make a plot area active by clicking on it. And I want to apply the coordinates tools at the top plot area, so I begin by clicking on it to make sure that it is the active plot area and that the run I want is active in the legend. And now I'll go back and add that coordinates or delta tool. The coordinates or delta tool has two parts. One is a gray box, and the center of the gray box, the coordinates of that point are shown in this label. And you can move these around separately. What you'll usually do is bring the gray box over a data point. It will snap to it. The label changes to the color of the run, telling you you're on that point, and it tells you the X and Y coordinates of that point in the center of the gray box. Well, there's another way to add a coordinates tool, and that's simply to go to a data point and click on it. And there's a pop-up that gives you an option for tools that are appropriate for analyzing a point. I got a coordinates tool there, and we could do the math to figure out what the change in velocity is from after the collision to before the collision. But there is an easier way. For that, I'm going to delete the second coordinates tool and click on the label of the first coordinates tool to reveal that there's actually another tool built into coordinates tool. This Greek letter delta implies that this is going to help us to determine changes. It is the delta tool. If I click on the delta tool, I get a second handle. I can drag out this second handle, and drop it on a second data point, I get the x and y coordinates of both the handle data points, but more importantly, I get a calculation of the change in x, in this case change in time, and what I'm looking for, the change in y, in this case velocity, between those two data points. So the delta tool, hidden within the coordinates tool, is a great way to determine changes in x and y coordinates between two data points. So I think I've determined the change in velocity of this cart during the collision, or from before and after. I'd now like to figure out, well, what was the impulse, the force over time? And for impulse, we need to calculate an area. Usually it's called area under the curve, but in this case, it will be area above the curve, that is between the curve and the y = 0 axis. And for that, I'm first going to make the lower plot area active by clicking on it. And then I'm going to go up and introduce a new tool from the graph toolbar. It's called the area tool. I'll click on it, and this is going to give me the area, quote, under the curve. Under is negative, over is positive. But you'll notice it applies to the entire run, and this gets to that question that was asked earlier, and that is, how do I analyze only a portion of the run, whether it's a curve fit, statistics, or the area tool? You'll notice over here that I'm actually also calculating the area under the curve for any portions that are outside the collision. So I want to analyze only the area under the curve for the collision portion of this. And for that, I'm going to go and introduce what's called the highlighter tool. Highlighter looks like a yellow highlighter marker. If I click on it, I'll get a box dropped onto the active plot area. And notice that all the data points inside the box are highlighted yellow, and the area tool updates to calculate only the area, quote, under those selected data points. I can move the highlighter. I can change its size by grabbing the handles. And what I'd like to do is adjust this so it's analyzing the area just during the collision, which I can see is -0.54, that's Newton seconds. If I want more decimal places, a grand trick in Capstone is to right-click. I'll right-click on this, look at tool properties, and I can actually change the numeric format to, say, ask for 3 decimal places. So this is how I can do an analysis of the changes in motion, the change in velocity during the collision, and the impulse during that collision. Now I could be writing these down in a lab notebook, I could be typing into Excel, but I'm going to show you I could also record this information, this meta information that I've gotten from analysis in Capstone by dragging a table in. So I'll go to the displays palette, I'm going to drag a table and drop it to the right of the graph. They begin by splitting the screen, and if I want the table to be smaller so I can still see the graph well, I can hover my cursor between the two and I get a dashed line that lets me adjust the size of both these displays at the same time. So now I could begin filling in this table with user-entered data. Tables can accept sensor data by choosing select measurement, or I can say, you know what, I'd just like to begin recording some of my own data into this table. I might say that this was a hard spring slow collision, and it creates a set of user-entered data, which I could rename to say this is the trial, and delete the units there. And I might next want to define the next cell to be the change in velocity. So I could type -1.036, hit enter. It creates another user-entered data set, which I can rename to be appropriate. I could call this change in velocity. I can be as verbose as I want. But remember the right-click trick. If I right-click, I can insert characters like delta. I'll make it concise, delta V, hit tab, and this will be in meters per second. Now I've run out of default columns, but I can go to the table toolbar, appears much like the graph toolbar, and insert another column, and I could record the impulse, the area under that curve, as -0.535, hit enter, and I get yet another set of user-entered data for which I can record J, and that's going to be Newton seconds. So you could see how this goes. I could record another run of data, change the bumper, I could go slower or faster, and I could do analysis for each of these runs and determine the change of velocity, change in impulse, and record that in the table in Capstone. I'm not going to waste your time by doing that. I have collected this data already. So let me open a Capstone file that I saved previously with 6 runs, 6 different trials. And all I did is do fast and slow collisions with the hard bumper, the hard spring rather, with a soft spring, with a clay bumper, and have 6 different collisions as indicated here in the table. And for each of them, I analyzed, just as we saw a moment ago, the change in velocity and the impulse. All right, so what can I do with this? Well, I'd like to analyze the results in a new graph. I've kind of run out of space here, so I'm going to build a new page inside my workbook by clicking this Add Page button. I now have page 1 and page 2. That's multiple workbook pages. I'm going to save some time by going to page 1 and clicking on the border of my table and choose Edit Copy, and then choose Edit Paste so I can have that table on the second page. And I'll move it over to the side, and I'm just going to drag a graph into this big open space on the right, and I can define my measurements to be, say, impulse on the y-axis. Impulse on the y-axis, and I'll choose change in velocity on the x-axis, and I can see that my 6 data points appear to lie in a pretty straight line. It's a little zigzaggy with those connecting lines because they didn't happen in time order here, so I'm going to right-click on a particular data point and choose to not show connecting lines. That just gives me my data points, and naturally now I would say, you know what, I wonder if this is a linear relationship. I can make a linear fit, and through a number of lines of evidence here, I can see that there appears to be a linear relationship between the impulse and the change in velocity, and through an analysis of the units, or recognizing that the mass of this system as measured earlier is 0.503 kilograms, I can get a clue that maybe this slope m actually represents the mass, also m by coincidence. So for 0.503 kilograms of cart mass, I'm getting a slope here about 0.508. So I could begin to conclude something like, let me bring this text entry box over here. I'm going to add a text entry box and say, our lab group, it appears that J is equal to, I can right click, delta V times M for mass, something like that. So there's a display that is not a data display, but is another way to record information in Capstone. So let me quickly save this file. I like to save all my files just to know that I can continue with them. So it's impulse and momentum analyzed. And I'm going to end this activity by showing you another way to get data out of Capstone that's not saving a Capstone file. And that is, sometimes we just want the data. So we can save a Capstone file for everything, or we could choose just to copy, paste data, or export data outside of Capstone for analysis in a data package like Excel, Google Sheets, or other data analysis packages. Now, if I have all the data I want in a table, I can select a cell in the table, press Control or Command A, and then go to the Edit menu and copy. And I happen to have Excel open here, so I could go and hit Edit Paste or Control V, and there's that data from the table ready to be analyzed in a different data analysis package. Now, sometimes you're not showing data in a table in Capstone, but you still want to get it out. In that case, you can go to the File menu and choose Export Data, and this dialog lets you control which data among the many different sets of data, whether it's sensor data or typed in user enter data, what you'd like to export in the form of either a comma-separated value file or a tab delimited file. Both of these are commonly used for data transfer across many different apps. I'm going to save it to the default comma-separated value and choose to export file. And this will be my Capstone data for the impulse momentum. And notice it's going to save as a CSV file. On my computer, this happens to be associated with Excel. So I'll bring that back on screen. Here's that exported data file. And if I double click it to open it in Excel, again, this will open in pretty much any data package. It's going to open up in Excel, and I will see that it is just all the data that I requested. So none of the displays, none of the analyses unless I typed it in. But if you just want data from sensors or from Capstone in another format that can be transferred across applications, choose to save it and export it as either a tab delimited file or a comma-separated value file. All right, we have one more activity. It's a quick one. Alec, as I set up for that one, any questions we can answer for the whole group?
Yeah, Michael had a question that I answered in chat about if you have data points at the beginning of or end of your run that you want to ignore or delete. There's a way you can do that easily in the graph. I wonder if you could show us.
Definitely, great question. So my data all happens to be pretty good here, but let's say I had a reason to suspect that this data point wasn't good, or these two data points weren't good. Whether it's data collected from a sensor or typed in, if you're visualizing it on a graph, what you can do in the graph is first notice my linear fit's applying to all the data points here. If I come into the graph and choose a highlighter and put that highlighter over the data points that I don't really want it to analyze, I have a tool that pops up here that allows me to exclude the highlighted data points. So I'm going to choose that. This isn't deleting them, it's just excluding them. And notice they're replaced by a little X there, they're scratched out in the table. But basically, if I turn my linear fit back on, this is now not analyzing I don't know if select, I have the selection here. So let me get rid of selection. I used it to get rid of the analysis. If I turn my linear fit back on, now it is analyzing all those data points, but not those. There is an option to delete data points using the same approach with this delete data button, but I find that since deletion is permanent, I often like to exclude the data points, and it feels like the better practice to me. But both of those are available, and thank you for the question. All right, so if you want to learn more about Capstone, for example, the graph tools I didn't go over, there is a Capstone help system. It's available on our website, or you can get to that website by simply going to the help button in Capstone and choose PASCO Capstone Help. It's going to open up in your browser, and you can both search through or browse through all of these topics, including things like how do I use all these tools on the graph display. Rest assured, we've introduced most of the key ones here, or the key approaches, but the help system is a great way to learn more about Capstone. All right. So we have just a few moments here to collect one more set of data using a different approach. And for this, we're going to look at this wireless pressure sensor and the syringe that's included with it. So this is out-of-the-box experiment that's available. And I have a little dilemma here. I want to determine what's the relationship between the pressure of the air in the syringe and the volume of the air in the syringe, which I can, of course, change by moving the plunger. How am I going to get the volume? Well, I can read the syringe label. Pressure is going to come from the sensor, but how in Capstone can I associate these two with each other so that I could find out if there's a relationship between gas pressure from the sensor and volume read from the syringe label? So we'll return to Capstone, and I'm going to choose File, New Experiment. Turn off my smart cart so that it doesn't reconnect. And we'll be able to go through this one quite quickly because we're going to take advantage of yet another of the startup options. Now, I didn't mention this earlier, but when I chose the sensor data button, there's actually a drop down here that gives me multiple options. When you choose the button, it chooses the first one, which was continuous sampling. That is, at the sample rate, the default sample rate or the one I selected, record data from all the connected sensors. There are other options for doing things like fast monitoring in a scope or looking at spectral display of FFT. But in this case, I'd like to choose the second option, which is from the tooltip to graph manual sampled sensor data versus user entered data. That sounds perfect for this investigation where I have user-entered volumes and sensor-based pressures. So let me choose that. It is, as always, going to prompt me to connect a sensor. So I'll turn on my wireless pressure sensor, connect to it, and now I can see that it has filled in pressure for the second column of the table and the y-axis, but the x-axis and the first column are just generic x. This is the user-entered data. I'm going to rename this because this is what I'd like to be the volume. The syringe is marked in milliliters, so I'll use that. And a subtle thing has happened here. Besides setting up this user-entered data against the sensor data, it has also put this file into what's called keep mode. So I'm going to show you that it's hidden this, but it's now in keep mode as opposed to what we looked at before, continuous mode. In keep mode, I don't have a record button. Instead, I have a preview button, and when I press it, basically, it tells me what the pressure measurement will be from the sensor, but I'm in control of when it gets recorded, allowing me to change the volume as needed and enter the volume. So if I started at a volume of 60 milliliters, I could put it at 60 milliliters, and then I could say, you know what? Let me put a little digits display here so I can see the stabilization even more clearly. Put it down here. Here's the current pressure reading. And when that is stable, I would like to keep that value. I can do that with the Keep Sample button that we see in the controls palette, and it keeps that value. It turns black, indicating that it has been recorded, and it advances to the next line. And in color, I can see that it's monitoring the next one. I can enter my volumes, my user-entered data at any time. Let me do that quickly here. I'm going to go down to 15 milliliters, which is about as much as I can do with one hand. And let me quickly go down. I'll go to 55, see that it's stable, press Keep, and notice that each time I press keep, it's recording the sensor values. Now, if you make a mistake, like let's say press keep twice, I can see the mistake here in the graph, and as long as I haven't stopped recording, I can return to that cell, which should have been at 45, go to the correct volume, press keep again. So I'm just going to quickly go down the line here, 40, keep, 35, keep. I can save myself a little time. If I put my cursor in that cell and make it active, I can now use the enter key or the return key to keep as well. So here's 30, 25, pretty stable, 20, keep, and final one, 15, keep. All right, now it's going to preview the next value, but I don't need it, so I'll simply press stop. And now I can see that I have a nice, definitely not linear relationship between pressure on the y-axis and volume. Very quickly I collected that data using this manual sampling technique. So we're going to wrap this activity up by looking at how we can determine the relationship here a number of ways. So I might want to turn off the connecting lines here. I'll right-click on a data point. And now I could ask students to take this data and figure out what is the mathematical relationship by using a curve fit. I might turn on multiple curve fits. Is it linear? Is it inverse square? Which of these curve fits seems to apply best to my data? Well, visually, I think there's a clear winner. I can also compare the root mean squared errors, which I can access here for linear fit by right-clicking. And I can see that among these three, the one that visually looks best is indeed the inverse, and that has quite a bit lower root mean squared error. So let me get rid of inverse square and linear. And I seem to be able to conclude that there is an inverse relationship between the pressure and the volume. So I've just discovered Boyle's law. Now, some pedagogical approaches like to use just linear fits. So let me show you that approach. I'm going to add another graph display by dragging it under this one. This is now a separate graph display. And for now, I'm going to mimic the top graph display of pressure versus volume. By the way, Capstone's smart enough that when I typed ML, it knows that it could probably convert that to other things. So if I wanted MKS units, I can switch that to liters. And I now have pressure versus volume, but if I suspect this is an inverse relationship, another approach I could take is to invert one of these axes. So I'm going to click on the volume, and not only could I change the measurement there, but I can choose quick calc, and I could square it, cube it, some common transformations. I'm going to take the inverse of volume, and now I can see that taking pressure versus inverse volume gives me what appears to be a nice linear relationship between the two. And I could turn on a linear fit and, of course, conclude the same things about this relationship between pressure and volume that I saw earlier. So there's the linear relationship, revealing the same relationship between pressure and volume when I'm analyzing pressure versus inverse volume. One more thing, this is a data transformation that's just visual in the graph, but we can also do data transformations that actually create new data sets that we can put in a table or other graph. For that, I'm going to go up here, and if this is indeed an inverse relationship, I should be able to take the product of pressure and volume. So I'm going to go here, and instead of adding an empty column, I'm going to add a new column to my table, which is a calculation. And in an Excel-like behavior, it allows me to basically say, what's this new calculation? It begins with the last column, pressure. I'm going to multiply that by right-click, insert data, volume. I'll put that volume in liters and hit enter. And now it is going to do the calculation of pressure times volume and create a whole new data set from it, which I could name, for example, PV, and that's kilopascal liters. I think that reduces to joules, but I'll just leave it as kilopascal liters. And now I could do an analysis here of the product. Is it fairly constant? I'll turn on statistics and I can see the mean, max, min, and fairly small standard deviation. So this calculation in the table has actually created a new data set. I can see it in the data summary under calculations. And a more advanced topic for a future session is this calculator allows us to do even more transformations even outside the table. But the one I just did of multiplying pressure times volume is created for me automatically in the calculator. Well, we've reached the end of our time here. Let me quickly tell you if you need to leave right now. I appreciate you being here. I will continue recording for the last couple of minutes here of resources. If you need to leave, though, please do so. We thank you for joining us, and there'll be a quick survey at the end. We appreciate your feedback on today's session, and you'll get the recording, including the little tag at the end by email tomorrow. However, if you are able to stay with us for a couple more minutes, I'm going to show you a couple more things. One of which is the question asked earlier, what if we just want to make a lab report? Well, an easy thing we can do in Capstone is to copy displays. So I'm going to click on my upper graph display. I might even make it larger. This is what I want to be in my lab report. So I'll click on the border of that display, go to Edit, Copy. It has now put that in the clipboard. And I might begin a report, let's say in Word. And here's the beginning of my group's lab report. And I can hit Control V or Command V. And I get that image pasted from Capstone into this report. Now, it's important to recognize this is just a static image. So I always recommend, it's a good practice to also go in and save your experiment as a Capstone file, should you want to do more analysis in the future. So hopefully that answers the earlier question. Thank you for that. You can also take screenshots, but Capstone has the ability to copy paste directly with displays. All right, so We've done some original experiments here so that I can show you how to set up Capstone, but rest assured that you can build your own experiments using the sensor data path, creating your own displays. There are some quick starts built into Capstone. I didn't use this, but if I were to connect my wireless pressure sensor, Capstone says, you know what? Lots of people like to use Boyle's law. So I can click on that and it will have a built-in Boyle's law activity that already has it set up for volume. So a little bit of time saving, but I wanted to show you generic manual sampling because there isn't a lab built in for every possibility, but there are quick starts built into Capstone. And finally, we have an experiment library at pasco.com/free labs. And if you were to go there and search for, say, Boyle's law, you could filter by equipment, grade level, Capstone file, and you might end up looking at our college level Boyle's law activity. That happens to be written for a different sensor, a different passport pressure sensor. There you're going to find two formats. There's a handout that's student ready, and there's also a Capstone file that has students work through this activity in Capstone itself. We haven't explored it, but I can add to Capstone images and texts and things like that in addition to the displays we've been using today. And this is an example of an experiment where we've done that and students can do the entire lab within Capstone itself. So, thank you so much for joining us today. If you want to get in touch with your local PASCO rep for further questions, to learn more about PASCO solutions, please go to pasco.com/support and you'll be able to figure out who your rep is, whether you're in the US or across the world. And with that, we will end our recording.